Right. Welcome to the first of the 5 lectures on this logic and database mini course of our bootcamp. Let me start with a quote, which you can also think as being the abstract for this. And this is that logic and databases are inextricably intertwined. And this was not uttered by a logician, but by a database person, one of the early pioneers of the relational data model, Chris Date. And the goal of this course is to pretty much convince those of you who are not familiar with the topic that indeed logic and databases are inextricably intertwined. In fact, over the past 45 years, there has been an extensive and continuous interaction between logic and databases. And the reason for this is that logic gives us a set of tools and also a unifying framework for formalizing, studying, and analyzing different data management tasks. And what I find myself particularly attractive, being a logician who moved to computer science, is that not only the interaction between logic and databases is a prime example of logic in computer science, but also it's an example of logic from computer science. And by this I mean that there are questions, problems, results, and methods that have motivated work of logic from considerations in computer science. If we reflect on what has happened during these 45 years, we will see there are 2 main uses of logic in databases. The first is that logic is used as a query language to express questions against databases. But there is a second use, and this is the use of logic as a specification language to express integrity constraints, semantic restrictions that the data at hand ought to obey. The emphasis on this course will be mostly on the use of logic as a database query language, and only in the last lecture on Friday, we will get to the second topic, which will be the use of logic to specify integrity constraints. This is a thematic roadmap that will roughly correspond, but not exactly, to the lectures this week. The first today is very, very elementary. It's mostly setting the vocabulary, the terminology, and making sure everyone is clear about the basic concepts. We will discuss relational algebra and relational calculus, and then conjunctive queries and their variants. Tomorrow I'll get to data log, but these languages, algebra, calculus, conjunctive queries, extensions of conjunctive queries, and data log will be examined from 3 different lenses, 3 different problems: the query evaluation problem, the query containment problem, and the query equivalence problem. And the lens here again will bring the tools from logic, decidability, and computer science computational complexity. If things go according to plan, on Wednesday we will look at some of the finer aspects of conjunctive query evaluation. Here we'll talk about more recent work about tree width, and even more recent work about estimating the size of natural joins and connections with linear programming. The last 2 lectures will be devoted to alternative semantics of queries. The first part assumes perfectly classical semantics, first-order logic or other logics with Tarskian semantics. But for practical reasons, alternative semantics have been discussed. We will discuss bug or multi-set databases, and we'll focus on the conjunctive query containment problem, which is an outstanding open problem in this area. And then we will conclude with probabilistic databases and the management of inconsistent databases. The emphasis would be on the query evaluation problem and the complexity of this, and the pursuit of dichotomy theorems that classify the complexity of these problems. And last but not least, we'll have a guest lecture on data provenance by Val Tannen, which is a very appropriate fitting, and I'm grateful to Val, who's a world expert on this, for closing actually this bootcamp on Friday afternoon with a talk on data provenance. So this is the thematic roadmap. But let's start in the beginning. How did it all get started? Relational databases were introduced by Edgar Code, or Ted Code, as he was known to his friends and colleagues. And at the time, he was at the IBM San Jose Research Laboratory on Cottle Road, which now has evolved to become the IBM Almaden Research Center. And in many respects, this is a history of both a scientific and technological revolution. The scientific revolution started with Code writing 2 papers that are technically very simple. They're conceptual papers, so don't look here for deep technical content, but turn out to be tremendously influential. The first was a relational model for data for large shared data banks in the communications of the ACM in 1970, followed by relational completeness of database sublanguages in a rather obscure volume in database systems. And the technological revolution, interestingly enough, started in this general area, in the Bay Area where we are. At IBM Research, the colleagues of Ted Code embarked on the development of System R that has become IBM's DB2 database product. Here at Berkeley, Michael Stonebreaker was a professor at the time, and he developed Ingress, another relational database model. And about 30 miles away from here, a rather dark figure by the name of Larry Ellison started Oracle. And this was kind of the beginning of the technological revolution that has made relational databases 45 years later quite a strong industry. The revenue for these companies is about $15 billion a year for the major vendors of relational database products. But as Professor Scott said in the beginning, we're not here to become rich, we're here to talk about science. So I want to move to what Code really did. So he had the notion that we can represent data as tables. And tables are just the mathematical relations that we tend to teach in our discrete mathematics course, that is a subset of a Cartesian product of sets. The only difference is that we give names to the columns. So for instance, we may have a checking table, and they have names indicating the data, the type of data that will go under each column. So that's an example of a checking table in a bank. So more formally, we have the notion of a relational database schema, which starts with the notion of a relation schema. And this is nothing else but what Anush called earlier in the morning a vocabulary, a relational vocabulary. So we have a symbol R that will stand for tables, except we also give names to the columns, and we call these attributes. And then an instance of a relation schema is just an actual relation that conforms to the schema. And then a relational database schema is a set of relation schemas of that form. And then an instance, a relational database instance, or simply a database, is a set of relations, each of which is an instance of the corresponding relation schema. In other words, it has the same number of columns, and that's that. So in some sense, if you come from finite model theory, you can say, what's the difference between a database and a finite relational structure? Because a relational structure is a tuple of this form. There is a universe and a bunch of relations, where in the relational database we have just a relation. So the difference is that in databases we don't make explicit the universe of discourse. And this causes some problems down the road, and we will see some of the difficulties that this causes a little bit later, but also we have ways to overcome this difficulty. So if you will, you can think of a relational database as a finite relational structure minus the universe. The universe is not made explicit. So let's go now at what Code did by way of introducing languages for querying relational databases. He introduced 2 different languages in terms of the philosophy of the design. One is relational algebra, which is a procedural language. And this is a formalism that uses algebraic operations on relations and expressions that involve combinations of these operations to retrieve data from the database. And he also introduced relational calculus, which, as we will see, is nothing else but a version of first-order logic. And it's a logical formalism that declaratively allows us to pose questions against the database. And his main theorem, which is in the second paper, is that relational algebra and calculus have essentially the same expressive power. This essentially requires an explanation, and it has to do with the fact that we have not made explicit domain, and I will make this very clear as we go along, I hope. Most probably, this was known to Tarski, but Codd maybe didn't know of the work of Tarski. I don't know the details of that, but in any case, he gets the credit for this result that says algebra and calculus have the same expressive power, and I'll explain what this means. Let's start with algebra. He based his formalism on 5 different operations. The 3 are perfectly general and set theoretic: union, difference, and Cartesian product of relations. The only restriction is for union and difference is that you have to apply to relations of the same arities, the same number of columns. So it has to be well formed this way. And then he had 2 special unary operations on relations that I will introduce: projection and selection. And then relational algebra consists of all expressions that you can get by combining these 5 basic operators in syntactically legal ways. So what's the projection operator? It has this syntax: pi, a sequence of integers, where these integers are distinct integers from 1 up to k, where k is the arity, the number of columns of the relation. And the semantics is, of course, that there is a tuple b1, bk in the relation such that the coordinates of the tuple that correspond to the indices are exactly the tuple a1, a2, am. So for example, if R is a relation with attributes a, b, c, and d, then the projection 3, 1 of R is the pair CA such that there is a BD so that A, B, C, D belongs to R. So intuitively, what this allows us to do is erase some columns and also permute the order of presentation of the columns. That's what it does. And we can reference it also with the attributes if we know what the attributes are. So these are 2 different syntactic ways to express the same projection. Please feel free to interrupt me if you have questions. This is an operation of columns, as you see. There is an operation on rows that has the form sigma theta r. R is the relation, sigma is the name of the operation, and theta is the condition. And this condition is a filter that applies to row by row. Some rows pass the filter, satisfy the condition, and they are kept out, they are kept in, the others are thrown out. So to give you the meaning of the semantics of this operation, I need to tell you what are the allowable conditions. In the simplest form that we will consider here, they are comparison operators, equality, and if you have an order on the domain of the elements, you can have less than or greater than, inequality, etc. And these are the basic atomic clauses, and then you allow Boolean combinations on top of these basic clauses in the selection condition. And then here is the full syntax of the relational algebra as a context-free grammar. We have names of relations, union, difference, Cartesian product, projection, and selection with the qualifications I described before. Now, when you look at these operations, each one does a rather limited task, but when you combine them together, they gain a lot in terms of expressive power. And this is the idea of derived relational algebra operations. So Codd wanted to make the language as economical as possible, but at the same time quite expressive. And the idea is that we don't need to define all the operations we need as primitives. We can obtain them from the 5 operations. For instance, intersection is conspicuously absent from Codd's operations, but intersection is nothing else but R minus S, right? So we can apply difference twice and get the intersection. When I teach this material in a database course, we spend the next hour giving a lot of examples of illustrating the expressive power. I will only give you one because it's very important for what it will follow. And this is the natural join. So suppose we have two relation schemas R and S, and they share some attributes. A1, A2, AK are the attributes that they have in common. Then R join S, this bow tie symbol, which in Latin is slash join, is the projection across a list of a selection of a Cartesian product. Let's look at the selection. The selection is a conjunction of equality conditions that tells you that the values on the matching attributes must be the same. And then the projection contains all attributes of R and Cartesian product with S except for S, A1, A2, AK. In other words, duplicate columns are eliminated. So we look for tuples that match, whose attributes match, and then we keep just one from the duplicate columns. To make it very concrete, the school year, the academic year had just started. And before the year started, departments, the university determined what faculty teach what course at what term. And then students enroll in courses in a particular term. And then out of this, we are interested who is taught by whom. So the taught by, which would be a relation with attributes student name, course, term, and faculty name, is nothing else but the natural join of enrolls and teaches, because you see the common attributes of teaches and enrolls are course and term, and we equate these two in the join, and then we take we keep only one through the projection. So that's the natural join operation. We will see lots of uses of it, and we'll analyze the natural join operation in very different ways. Now, I said that code was interested in having as few operations as possible. So one natural question to ask from a language design is, do we need all five? In other words, can we express one of the five in terms of the other four? And it's a very simple result, but I think fundamental result, that these operations are independent of each other. There is no way to express one in terms of the other four. How is this something like this proved? The proof idea is that we have to identify a property that is shared by any four of them, but not by the fifth one. And some of them are very easy to see. For instance, the Cartesian product is the only operation that increases arities of relations. So by induction, you prove that combinations of the other four operations maintain, they don't increase. It's less than or equal the arity. So that gives you for the projection. Okay? That gives you the Cartesian product. The projection is the only operation that may reduce arities. The difference is the only non-monotonic operation in the second argument, R minus S. Okay? And you have to think a little bit more carefully to see what to do with the union and the selection, so I will leave this as an exercise. But I think from the design point of view, Code apparently was a very careful and frugal man, did not want to introduce unnecessary operators. And indeed, this choice is very wise in some sense. So that's the story of relational algebra. And once you have this, you can give semantics of SQL, which is the standard commercial query language, stands for structured query language, to relational algebra. The basic construct of SQL is select from where. So as an example, you may have select r1.a1, rm.am from r1 rk where, and the semantics is the following. The from indicates a Cartesian product. So you form the Cartesian product of the relations in the from list. The where is a selection condition. So you do a selection, and then the select is unfortunate mismatch of names. It's a projection. Okay? But rather than having to understand the compound statement select from where on its own, here you can see it as a one-liner, as an interpretation of the basic structure of SQL into relational algebra. SQL also supports separate union and difference, and the conditions in the where can become very, very elaborate, but in its basic form, this suffice for now. Okay, so we have seen how SQL in the basic construct can be interpreted to relational algebra. So with this, let's turn to relational calculus. So as I said, Code introduced relational calculus, and it's really first-order logic suitable for databases. He presented it in two different forms, tuple calculus and domain calculus. The difference is whether arrays are first-class citizens or elements of arrays are first-class citizens. That's the only difference. I will talk here about domain calculus. This is more familiar to logicians, and there is an easy translation between the two formalisms. And again, as I indicated earlier, his main result was that algebra and calculus are equivalent formalisms as regards expressive power. This is the syntax of relational calculus, but just first-order logic. We have first-order variables. We have relational symbols. We have atomic formulas. But we also have atomic formulas that involve equalities, inequalities, or less than if our domain supports that. And we can also say, we have constants. We can say this variable is equal to a constant or not equal to a constant. And then we build the standard syntax of first-order logic with Boolean connectives, existential and universal quantification. How did Code use calculus or first-order logic as a database query language? Well, in effect, he had the idea that you can use uniform definability. It's very close. It's essentially the same as what Anus called the property. You can define a property. But now we come from the syntax. So a relational calculus expression is an expression of the form braces x1 xk such that phi x1 xk, where phi is a relational calculus formula with this as its free variables. And the idea is, this is a program, and you run it against every database, or any database you are interested, and you look at the tuples, a1, ak, that satisfy the formula on your database. And then you collect all these tuples together. So this is really uniform definability idea that you apply to the databases of interest. As a concrete example, if we write this expression, xy such that there exists z, exz, and ezy, this gives the set P of all pairs of nodes that are connected via a path of length 2. So when you run it on a relation E, think of it as a graph, it gives you all the pairs AB that are connected via a path of length 2. And again, the Code's theorem, informally, is that algebra and calculus have the same expressive power. In other words, they can define the same queries. But this statement is not true, as I stated it. The reason is that while you can translate easily algebra to calculus, you cannot translate calculus to algebra always. For instance, if we have allowed in our syntax this expression, this is a perfectly meaningful relational algebra expression that gives us the tuples that are not in R. But remember, we have not made the domain explicit. So what does this return? Or this one, x such that for all yz enrolls xyz. What is the universe over which we are interpreting the universal quantifiers? So this is the problem, and this is the problem caused because the domain is not made explicit. So the problem with these two last expressions I showed you was that they may produce different answers when we consider different domains over which the variables are interpreted. And another way to put this is that the meaning of formulas like this depends on the domain over which you interpret the variables, as opposed to something like this. This is the calculus expression that gives the difference of S minus R. That's domain independent, okay? Because the tuple here, x1, xk, is in S, so it's guarded by S. and the meaning is unambiguous. Once you realize this, you see what the fix is. The fix is to bring into the picture the so-called active domain. Think of it as being the active universe of discourse. So you have a relational database. This is just a bunch of tables. But the tables have tuples, and the tuples consist of values. So it's the set of all values that occur in the relations of a database. Now, if we take a relational calculus formula and we have a database, the database is just a bunch of tables, we can consider phi in the active domain of D is the result of evaluating this formula over the active domain of D and D. In other words, we look at the relational structure that has the relations as relations, database as relations, and has as universe the active domain. And now we use Tarskian semantics, and that's the result of the evaluation. Now, with this concept, evaluating the formula on the active domain and on the database, we can get a very precise statement, and that's really what Code proved, that if I have a Chiari query, a property, which on every database gives us a Chiari relation, then the following statements are equivalent. There is a relational algebra expression that returns this relation on every database, or it's equivalent to having a relational calculus formula such that the result of the query on the database is the result of evaluating the formula on the database with the active domain semantics as the universe of discourse. So now this is a clean and precise statement of what Code really proved, and it is in this sense that algebra and relational calculus are equivalent in terms of expressive power. This has an easy proof. Going from algebra to calculus is a straightforward induction, and it won't come as a surprise as I tell you that projection is existential quantification. Okay. Going from calculus to algebra, it's also easy. All that one needs to observe first is that the active domain can be expressed in relational algebra. And this is very easy because the active domain is the collection of all values that occur in relations in the database. So what we do, we take all the projections of every relation and we take a big union of everything. So that's a union of projections that gives us the active domain. Using this fact that we can express the active domain in algebra, then we can do induction on the construction of relational calculus formulas to obtain the translation. And I will only illustrate this by showing how the universal quantifier can be simulated in relational algebra. Not surprisingly, it uses the basic logical equivalence that for all y psi is not exist y not psi. So for example, consider the expression for all y rxy, which by the way is domain dependent. So it's one of these that we have to worry about. We rewrite it as not exist y not rxy. And now, because it's a binary relation, the active domain is the union of the two projections. And then the negation of this relative to the active domain is the Cartesian product of the active domain with itself minus r, the difference. The existential quantification of this is the projection. And then the negation of the existential quantification is the relative complement with respect to the active domain. So this is a relational algebra expression that on the active domain expresses this query. Questions?
Yeah, it shows why we don't program using logic.
If there were another relation present in the database that had nothing to do with this formula, that would affect the active domain and would affect the meaning of that query, right?
If we had another, yes. So this assumes that the active domain restricted to the, yes, thank you.
So this means that queries get worse when you transfer from first-order logic into relational algebra? Any results known, or is that?
No, the translation is linear. So the translation is linear. It's ugly. It's ugly, but it's linear. On the other hand, why don't you complain about SQL that doesn't use universal quantifier, use exist and not exist, right?
universal quantification in SQL. It's just
It's not exists.
widely used.
It's not exists. Yeah, but students have a hard time writing such
Say
queries.
all.
Okay.
So it seems very natural, and I guess it's a question whether Cod considered this already. It seems very natural to associate different types to different attributes, and to have, for example,
Yes.
the operators that, for example, there might be some type of strings, and you have certain operators on strings and so
Yes.
forth. Whereas
I simplified here. I suppressed the types.
Okay.
The domains, of course, in SQL, when you declare a relation, you have to say type integer, type string, etc. Right? I have suppressed this for the purposes of this presentation.
and when Cod originally formulated his
He wasn't. No, he had it about the same level that he have. The paper was really a paper in logic, and he focused on this translation. Yes.
And so I imagine soon thereafter, you know, the type structure of all these things was incorporated.
Correct. Thanks. Yes. All right. So we have seen this translation of algebra to calculus and calculus to algebra, and let me just formalize, because I mentioned queries. Formally, a query is a function defined on database instances, so that if I have a database instance of arise, then Q of D is a carry relation. That will be a carry query. And we want the invariance under isomorphisms. That's exactly what Anuj was talking earlier in the morning. And a Boolean query, that captures the concept of a property in Anuj's talks, in Anuj's talk, is a function defined on database instances such that either we get answer 0 or 1, the query is true or false. And again, this has to be invariant under isomorphism. So that's the notion of a query. And of course, questions like the diameter at most 3 is a Boolean query, the graph being connected is a Boolean query, and so on. All right. Now, so what have we done so far? We have basically introduced the Code's formalism and two formalisms, and we saw the basic equivalence between them modulo these active domain considerations. There are three fundamental algorithmic problems that people looked in database theory. The first one is basically the most fundamental problem in some sense. That's what database systems do. You write a query, you run it on a database, and you get an answer. So this is the query evaluation problem. As we have phrased it here, both the query and the database are part of the input. And we'll elaborate on this as we go along. Now, a different problem, but important in the query evaluation problem, is the query equivalence problem. And this is if I give you two queries of the same arity, or if give you two Boolean queries, is it the case that they're equivalent, meaning is it the case that on every database they return the same relation? This problem is important in the query evaluation problem because when a programmer writes an SQL query, what happens is that this gets internally translated into a relational algebra version, but that's not what's executed. There is a sequence of transformations that try to produce an equivalent query, which is presumably less costly to evaluate using the database engine. So in some sense, this underlies the principles behind optimizing query evaluation. In turn, the query equivalence problem is related to the query containment problem, which is given two queries Q and Q prime, is it the case that Q is contained in Q prime, which means is it the case that for every database instance D, Q of D is contained in Q prime of D? Is it the case that Q prime of D, Q prime is an over-approximation of Q on every database? And of course, as I said, query evaluation is the main problem in query processing. Equivalence underlies query processing, as we often transform a given query to an equivalent one. Query containment and evaluation are really very closely related because equivalence is containment both ways, but also containment is reducible to equivalence since containment amounts to the equivalence of Q with Q and Q prime. So you can think of equivalence and containment in this context as being the same problem. We will see later on when we talk about bug semantics that this is no longer the case there. So we have these three fundamental algorithmic problems. And the question is, what can we say about their algorithmic properties? And we have the first piece of bad news, that as regards relational calculus or relational algebra, query equivalence is undecidable. And in fact, you know the answer to this, because in the morning, Anush mentioned Trachtenbro's theorem, which in some sense is one of the very early results of finite model theory. And it's an anti-completeness theorem, it's anti-Gödel completeness theorem. It says that the set of finitely valid sentences are undecidable. They're not even recursively enumerable. It's a coarse set, but it's not recursively enumerable. In particular, it's not recursive. So these are the first order sentences true on all finite graphs A. And then finite validity has a very easy reduction to query equivalence, because you take some fixed finite relational calculus sentence, and then if you take psi star, if you take some other relational calculus sentence phi, we have that phi is finitely valid if and only phi is equivalent to psi in the finite. So Trachtenbrod's, which by the way, this was part of Trachtenbrod's the doctoral thesis in what at the time was the Soviet Union in 1949. So we get the undecidability of the finite validity problem. And as a corollary, the query containment is also undecidable. So query equivalence has this easy reduction to query containment. So we get here through Trachtenbrod that both equivalence and containment are undecidable. So you can think of this as bad news, but as we will see, the silver lining is that this will also drive the quest for identifying fragments of algebra or calculus on which these problems have better computational behavior. So we have talked about three problems: query evaluation, query containment, query equivalence. Equivalence and containment undecidable. What can we say about the query evaluation problem? And here we have decidability but high complexity. So the query evaluation problem, again, is given a relational calculus formula and a database instance, find phi, evaluate on the active domain of D. And the basic theorem there is that the query evaluation problem for relational calculus is p-space complete. This was known in the early 80s. So practically everything I'm saying today was already known in the early 80s. So there is really nothing very, very new here. It's a very basic and important result. I will sketch the proof of this. We need to do two things. One is that it is in polynomial space, and the second, that it is hard for polynomial space, meaning every other problem in polynomial space has a reduction to it. We will start with the second task because it's easy, modulo a very important result about p-space. So back in 1976, Larry Stockmeyer at his PhD thesis at MIT produced the first problem that was complete for polynomial space, and this is quantified Boolean formulas. A quantified Boolean formula is a propositional formula in front of which you have a bunch of quantifiers. And the question is this true? When you interpret it as a two-person game that they play bits, and at the end you test whether the string produced makes the formula true. And there is a very easy reduction of quantified Boolean formulas to the query evaluation for relational calculus. And the reduction is that you basically take two unary relations and you replace the variable xi by the atomic formula p of xi and the negation of the propositional variable xi by the negation of p of xi. And then you look at this little database instance that has these two relations, v is 0 and 1, and p is 1. And then, of course, you have that this Boolean formula, this quantified Boolean formula is true if and only if this relational calculus formula is true on the database that consists of v and p. So it's a very simple reduction. In fact, what this reduction shows is that if you have any finite relational structure which is non-trivial, there is one relation which is not empty and is not everything, then the first order theory of this structure is polynomial space hard. That's what this really shows. So in particular, we get that the query evaluation problem for relational calculus is p-space hard. What about the membership in p-space? At first sight, if one gives you a first-order formula like this, and you have a database instance, there is an obvious exponential time algorithm. You exhaustively cycle over all the possible interpretations of the variables. And this runs in time n to the m, where n is the size of the database, let's say the size of the active domain, and m is the number of quantifiers, the number of variables you have in the formula. So the naive algorithm is exponential time. But then you can do some careful bookkeeping and get it down to be in polynomial time, in polynomial space. And wow, OK. That'll be wonderful, yes. That's the famous and rich part, I mean, as Dana Scott would say. So a more careful analysis shows that this can be implemented using space big O m. M is the number of variables log n, n is the size of the database. And what is the idea? The idea is simply this. You have m blocks of memory. These stand for the quantifiers. And in each block of memory, you write down in binary different elements from the active domain. And then you cycle through this. And you also need to do some bookkeeping. And the bookkeeping is you have to maintain counters, as many counters as variables, to keep track of the number of elements examined. Okay. But again, you need only logarithmic space since you have polynomially many elements. So if you do this carefully, I'm only sketching here the idea, it's a p-space implementation of the exponential time algorithm. So now we have, as corollary, also getting that the query evaluation problem for relational algebra is p-space. This goes back to a question that I was asked before. The translation from algebra, from calculus to algebra that we saw before, it was ugly, right? But it was linear time. So this gives us for free the p-space hardness and the p-space completeness of the query evaluation problem for relational algebra. So what is the summary of what we have seen so far? That the query evaluation problem for calculus or algebra is p-space complete, equivalence and containment undecidable. Now let's take a somewhat closer look at the source of exponentiality for the algorithm we saw before for the evaluation, for the query evaluation. So as I mentioned before, the p-space algorithm was a careful implementation in polynomial space of the exponential algorithm. The running time is n to the m, where n is the size of the database and m is the number of variables. So really, the source of the exponentiality is the formula size. The source of the exponentiality is the formula size. And this tells us that if you fix the formula, if you only care for one query, then you are in polynomial time. That's an immediate consequence of this, because now the formula has fixed size. But if you take the previous algorithm, the p-space algorithm, and now you do it with respect to a fixed formula, then this uses logarithmic space because m, the number of registers that you need to maintain, is constant, right? And what you put in each of them is logarithmically big in the size of a database. So we get a very important fact that for every fixed relational calculus formula, the query evaluation problem is in log space. And typically, in databases, we have a relatively small query and a big database, as opposed to, say, in something like satisfiability, where we have a small database, that's essentially a Boolean database, but the formulas are big, right? So with these considerations in mind, back in 1982, Moshe Vardi, who at the time was just finishing his PhD, published a paper in Stock that has become very influential, and it's called The Complexity of Relational Query Languages. And he took these observations that we made before and created a taxonomy. The taxonomy says, suppose you have a database query language. You are interested in the query evaluation problem, but we are going to slice it and examine it in 3 different ways. The more general way is to look at the so-called combined complexity, where both the sentence and the database instance are part of the input. And the question is, does the database satisfy the sentence? So here both the database and the sentence are part of the input. But now we can, since we have 2 parameters, we can get to families of decision problems by fixing one of the 2 parameters. If you fix the sentence and you let the database vary, you get the so-called data complexity of L. So this is a family of decision problems, 1 for every sentence. And the problem is, given a database instance, does the instance satisfy the sentence? Again, a family because we have 1 for every sentence. Now we can turn things around. We can fix the database and let the queries, let the formulas of the language be the input. So given an L sentence, does the database satisfy? This it's a family of problems, but now it's parameterized by the database before it was parameterized by the formula. So what Vardi did in this paper, other than introducing these concepts, was to also introduce what it means for the data complexity problem and the query complexity problem to be in some complexity class and to be complete for the class. So, okay, the data complexity problem is in some complexity class if for every sentence phi, the corresponding decision problem is in the class. And we say it is complete for the class if it is in C, meaning for all the sentences it is in C, but there is at least 1 sentence for which it is C complete. And analogously for the query complexity, we say the query complexity belongs to some complexity class if for every database D, the decision problem given a sentence, is it satisfied by the database is in C, and we say the query complexity is C complete if it is in C and there is at least 1 database for which it is C complete. And Vardi then went on to examine a whole bunch of query languages, and he made an empirical discovery that for the language that he considered, there was a gap. Typically, the data complexity of a language is of lower complexity than both the combined complexity and the query complexity, and often the query complexity is as hard as the combined complexity. And in some sense, this is a picture to see where things stand. Log space is down here, P space up there. In between, we have non-deterministic log space, P and P, polynomial hierarchy, and other things. From the classical hierarchy theorems, we know that log space is properly contained in P space. That's the only separation we know. So somewhere here, these things 2 consecutive levels must be different, but we don't know where the difference is. And as regards calculus, we have this rather complete understanding at this level, of course. Combined complexity is P-space complete. Query complexity is P-space complete, which means it is always in P-space, and there are some queries for which it is P-space complete. Data complexity is in log space. So that's the gain, the analysis we get out of this. Questions? All right. So again, the summary is algebra and calculus have essentially the same expressive power. That's Codd's theorem. Query equivalence, query containment for relational calculus, undecidable. Query evaluation is P-space complete in combined and query complexity, and log space for the data complexity. And of course, all these now raise the question, are there interesting sub-languages of relational calculus for which the query containment problem and the query evaluation problem are easier than the full calculus? Can we find interesting fragments? And the answer is yes. In particular, the language of conjunctive queries, which I will introduce today, but we'll continue the discussion next time, is such a sub-language. And what is special about the conjunctive queries is that these are arguably, if not the most frequently, at least among the most frequently asked queries against relational databases. So what I want to do next is to introduce these conjunctive queries and look at them from very different perspectives. And then next time embark on the problem of analyzing these problems, query containment, query evaluation, query equivalence for the class of conjunctive queries, and then for extensions of conjunctive queries with other syntactical features. So a conjunctive query is simply a query given by a first-order formula, a bunch of existential quantifiers followed by conjunction of atomic formulas. They are well known to logicians. Sometimes these are called primitive positive formulas, and they play an important role in our discussion. Let me give you some different perspectives to this. You can think of them as being the queries that are expressible in relational algebra by a projection of a selection of a Cartesian product where the selection condition is a conjunction of equality atoms, equality atomic formulas. It is what we often call an equijoin in databases. Equivalently, if I were to write them in SQL, I mean, in some sense, SQL is made just to support conjunctive queries at the first level. A select list of attributes from relation names where conjunction of equality. So the conjunction of equalities is this selection condition, and the list of attributes are the variables that are not existentially quantified. So that's the translation between conjunctive queries and SQL in this form. We can also write them as a logic programming rule. When you write them as a logic programming rule, you replace the conjunctions by commas, and you suppress the existential quantifiers. And the idea is that if you have a variable that occurs in the right-hand side, but that in the left-hand side, that variable is existentially quantified. The right-hand side is called the body of the logic programming rule. The atom on the left is called the head. And as I said, the existential quantifiers are not displayed. They are suppressed, and they are inferred because they stand for the variables that appear here but not there. So let's look at concrete examples. We saw before the query path of length 2. That's how you write it as a conjunctive query in calculus. As an algebra expression is the projection on the first and the fourth, where you insist that the second and the third attributes have the same value. As a rule, you write it like this. Z is not occurring here, therefore it's existentially quantified. Conjunction replaced by comma. Cycle of length 3, same idea. As a rule would be now no variables here, therefore all the variables are existentially quantified. Notice that every natural join is a conjunctive query with no existentially quantified variables. So for instance, if I have these two relations, ABC, R, P, ABC, and R, B, C, D, then the natural join of P with R is X, Y, Z, W, such that P, X, Z, and R, Y, Z, W. This would be written as a logic rule, and this would be written as in SQL. So we have different ways to look at conjunctive queries. And they are also known as select, project, join queries, exactly because of this way to write them. So now we come to the point that we're going to revisit these questions we had. So these are the general questions about evaluation and containment at the level of conjunctive queries. So conjunctive query evaluation, I give you a conjunctive query and a database, evaluate the query on the database. Conjunctive query containment, I give you two conjunctive queries. Is it true that Q1 is contained in Q2? At the level of Boolean queries, this is just a logical implication, because it means, is it true that for every database that satisfies the first, the database also satisfies the second? So think of conjunctive query containment as generalization of logical implication for conjunctive queries. And we also have the problem of conjunctive query evaluation. And recall our discussion that for calculus, the query evaluation was p-space complete, the query containment is undecidable. What happens if we go to conjunctive queries? So we have a very basic theorem by Chandra and Merlin from the Stock Conference in 1977. This was the good old times that database theorists could publish a paper in the Stock Conference. That's no longer true. And they pointed out that conjunctive query equivalence and conjunctive query containment are really the same problem from what we have seen before. These are very different problems. At the level of calculus, one is undecidable, the other is p-space complete, right? But they amount to the same problem, and moreover, they are both NP complete. They are the same problem, and this problem is NP complete. So in some sense, this tells you a trade-off. You lose in expressive power. You go from relational calculus to conjunctive queries, but you gain in complexity. Okay? You gain in complexity because you drop from p-space and undecidable to NP complete. Now you wonder how this is possible and what is the glue, what is the common link, what do these have to do with each other, and the common link is the homomorphism problem. It's the homomorphism problem. Look, if you are a mathematical logician and you look at Wilfried Hodge's book, it's one of the exercises is this theorem there, right? But these were computer scientists. They were sitting at the IBM Watson Research Center. They're doing databases. And they came up, they realized that this is the connection, and they wrote this very famous paper by now. So let me remind you what a homomorphism is. And we have here the benefit of having Professor Nesetril, who has written the book on graphs and homomorphisms. But anyway, if we have two database instances over the same schema, a homomorphism is a function from the active domain of the one to the active domain of the other, so that this function preserves membership in relations, meaning if you have a tuple that belongs to a relation in P, then the image of the tuple under this function belongs to the corresponding relation in the other database. Clearly, it's a relaxation of the concept of an isomorphism. Every isomorphism is a homomorphism, but not vice versa. One of the most striking examples is that from the homomorphism perspective, graph free colorability that we saw earlier in the morning is the property of the existence of a homomorphism from the graph to K3, that's the clique with the three elements, that's the triangle, right? And the homomorphism tells us what color to assign to each node. And it also, this condition guarantees that edges go to edges, which means that no two edges end up with the same color. So three colorability is the existence of homomorphism to K3, two colorability is the existence of homomorphism to the edge, and so on and so forth. K colorability is the existence of a homomorphism to the K clique. And the homomorphism problem asks, given two database instances, is there a homomorphism from one to the other? And this notation, D arrow F, denotes the existence of a homomorphism from D to F. And it's very easy to see, in fact, you already saw it, that the homomorphism problem is NP complete, because a graph is three-colorable if and only if there is a homomorphism from G to K3, and three-colorability is NP complete. In fact, we see that it is NP complete even if we fix a particular F, in this case, the clique with three elements. As an exercise, if you have not seen this before, try to express three satisfiability as a special case of the homomorphism problem. So I should say that the homomorphism problem is a very fundamental algorithmic problem. We saw that the colorability problems can be viewed as a special case of it, homomorphisms to cliques. You can write satisfiability, three satisfiability, not all equal three satisfiability, positive one in three satisfiability as special cases of it. That was part of the exercise I mentioned yesterday in the previous slide. Many AI problems, such as planning, can be viewed as special cases of the homomorphism problem. And in fact, there is a rather influential paper by Thomas Feder and Moshe-Vardi, 1993, where they argued that every constraint satisfaction problem can be viewed as a special case of the homomorphism problem. So in effect, you can give an algebraic account of constraint satisfaction as the homomorphism problem. And I'll return to this point in subsequent lectures. So the main theorem that we're going to discuss next time is that the conjunctive query evaluation and conjunctive query containment are the same problem, and moreover, each of them is an NP problem, and the link would be that they are equivalent to the homomorphism problem. And to establish this link, I'll bring next time two basic notions: the canonical conjunctive query of a database and the canonical database of a query. And once we have these concepts, we'll be able to give a self-contained proof of this result. So, being 4 o'clock, it's time for a break. Thank you. Questions?
Yes.
No, some.
The data complexity problem you said was in log space but not complete. Is it actually log time hierarchy?
It is in AC0.
AC0, yes,
So it is log. It's log. Yeah. It's log. It's not log space complete.
Right. Well, that's the same as log time hierarchy, I guess.
Yeah. Exactly. Yeah. No, I didn't say it can be.
Probably doesn't have a complete problem.
Yeah, that's exactly right. Break time.